Right, let's have a look at our first linear model. What do we know about houses? We know that I can't draw them very well, but the chances are that as the house gets bigger, the price gets more. So we might expect something like, well, that's a start. Let's be slightly more academic about this. We might say something like price equals some intercept term plus the gradient times lot area plus some unexplained error term. There are two terms that we don't know, the intercept and the gradient, how much the price goes up with each increase in lot area. If we could find out beta 0 and beta 1, we might represent them with a little hat, and then we could make predictions. We would say that the predicted price is going to be beta 0 plus beta 1 times the lot area. When we make a prediction, we don't know what the error is. How do we go about finding beta 0 and beta 1? If we were statisticians, we might use something called the normal distribution. The distribution of x, given its mean and its variance, is equal to some stuff which we won't write, followed by the exponent of minus 1 over 2 sigma squared x minus mu squared. Why do we care about that? If we were taking a statistical approach to estimating beta 0 and beta 1 with the Amy's house price data, we might say something like this. Well, we actually know what the price is for a given house, and we also know what the predicted price is for a given house. And if our model is good, then the likelihood of that difference should be small. Now, the likelihood is given by, so the likelihood is proportional to this. We want to make the likelihood as big as possible. Well, we need to make this lot here as small as possible, which means we need to make price minus prediction squared as small as possible. That will make the likelihood as big as possible. Or to be precise, we need to make the sum of these errors over all our observations as small as possible. The machine learning approach isn't necessarily directly interested in statistical distributions. What we do with machine learning is to choose a loss function and minimize it. We might simply say that if we have, for each observation, we have the price and we have the prediction, we might want to minimize the sum of the absolute errors, or we might want to minimize something to do with the sum of the percentage errors. Or we might indeed want to minimize the sum of squared errors. If we are doing machine learning and we choose to minimize some of the squared errors, that is equivalent to the standard statistical approach, maximizing the likelihood of a model based on the normal distribution. What is then the difference between machine learning and statistics? Well, I think with machine learning you are freed a little bit from having to think only about one particular distribution. Instead, you can think, what loss function makes sense for me to minimize? In the case of Amy's house pricing, for example, does it make sense to minimize the sum of squared errors? We'll probably talk about this another time. Does it really make sense that an estate agent, when using a model, would want to use a model built on minimizing the sum of squared errors? I'm not so sure that it does. I'm not sure how easy it was to follow along with everything I just said, but where we've ended up is that we have a model, which is that our prediction is going to be equal to some intercept plus slope times the lot area. And we have to estimate these two things. And the way we are going to estimate them is by minimizing the sum of the squared errors. Actually, equally, we could minimize what's called the mean squared error, which is equal to 1 over the number of observations times the sum of the squared errors. And the sum of the squared errors is going to be the actual price minus the predictions squared. How do we go about minimizing this lot? Well, what we're going to try to use is gradient descent. If you remember, for gradient descent, we need to know the gradient. Let's try and work out the gradients. To make our lives simple, I'm just going to start a new page here. The mean squared error equals 1 over n. I'm going to change how I show this a little bit. I'm just going to say it's 1 over n times the prediction error squared. And let's not forget, the error equals price error I equals price I minus the prediction, which is beta naught plus beta 1 times lot area. Now, we're going to differentiate the mean squared error with respect to beta naught. We will get 2 over n times the sum I equals 1 to n of the error times the differential of error with respect to beta naught, which is just minus 1. If we do the same with respect to beta 1, we will get 2 over n, sum of the errors, times the differential of the error with respect to beta 1, which is minus the lot area. I've just written this out a little bit more clearly. What does this mean with regards to gradient descent? Well, do you remember, with gradient descent, we find the gradient and then we move in the opposite direction. So let's take the first term over here. There's a minus sign in front of it. So to move in the opposite direction, we're going to move in this direction. What does it mean to move in this direction? Well, if that is positive, it means that across all observations, the price is greater than the prediction. So what would we do in such a situation? We would increase the intercept to try and make our predictions bigger on average. So gradient descent would do exactly the right thing. How about this term over here? What does it mean to move in this direction? Well, this is the direction we move with regards to the gradient. Now, the term inside the sum sign is actually the correlation between our errors and the lot area. Now, if there's a positive correlation between our errors and the lot area, we need to make the slope steeper. And that's exactly what we will do, what we would do in this situation to beta 1 when we move in the direction of the gradient. That's all we need for now. We are now going to go across to Python and implement gradient descent for Amy's house pricing in Python.